Connectionism, also known as the biologically inspired or physiological approach, involves emulating the human and animal nervous systems. The advancements in modern neurophysiology have provided inspiration and impetus to connectionism, making it, to some extent, an interdisciplinary science. Connectionism aims to achieve machine learning and cognitive functions by simulating the connections and information transfer between neurons. It has the following characteristics. 1. Neural network structure. Connectionism adopts neural networks as its basic model. Neural networks consist of numerous simple nodes, neurons that exchange information through connections. The connections between layers form the network structure, where information flows from the input layer to the output layer. 2. Learning and adaptability. Connectionism emphasizes the system's learning and adaptability. By adjusting connection weights, neural networks can learn patterns and regularities from data. This learning is often based on feedback signals, adjusting weights based on the difference between output and expected results. 3. Distributed representation. Connectionism advocates using distributed representation to store and process information. Unlike symbolic AI's centralized representation, distributed representation scatters information across nodes in the neural network, enhancing system robustness and generalization. 4. Parallel processing. Connectionism systems simulate the parallelism of the human brain by processing large amounts of information concurrently. Neural network parallelism enables the system to handle multiple inputs and perform multiple tasks simultaneously, enhancing overall efficiency and speed. 5. Self-organization and adaptability. Connectionism systems possess self-organizational and adaptive capabilities. During learning, neural networks can autonomously adjust connection weights to adapt to different input patterns without explicit programming. 6.
Nonlinear mapping.
Connectionism emphasizes achieving complex function approximation through nonlinear mapping. The introduction of activation functions with nonlinear elements in neural networks allows them to learn and represent more intricate relationships and patterns. In the early development of connectionism, several individuals made outstanding contributions. 1. Frank Rosenblatt, founder of the perceptron model, proposing the perceptron learning algorithm. Despite later limitations and criticisms, the perceptron played a pioneering role in the development of connectionism. 2. David Rumelhart collaborated with James McClelland and others, proposing and developing the backpropagation algorithm, a crucial method for training neural networks. His work had a significant impact on the development of connectionism. 3. James McClelland, a pioneer in connectionism and parallel distributed processing. McClelland, along with David Rumelhart, co-authored the influential book Parallel Distributed Processing: Explorations in the Microstructure of Cognition. 4. John Hopfield introduced the Hopfield network, a feedback neural network used to solve optimization problems, playing a critical role in connectionism. In the recent wave of deep learning and reinforcement learning, the following individuals played key roles. 1. Geoffrey Hinton, a foundational figure in deep learning. Hinton made significant contributions to the development of connectionism. A leading figure in the field, he proposed various deep learning models and algorithms, including convolutional neural networks (CNNs) and capsule networks. 2. Jan LeCun, a pioneer in deep learning. LeCun's research on convolutional neural networks (CNNs) had a profound impact on tasks like image recognition. He is also an advocate and promoter of deep learning. 3. Yoshua Bengio, one of the three giants in deep learning. Bengio made outstanding contributions to deep learning and connectionism. His research covers areas like recurrent neural networks and generative adversarial networks. Connectionism and neural networks have several notable advantages. 1. Learning capability. Connectionist models exhibit strong learning capabilities. By adjusting the connection weights of neural networks, the model can learn complex patterns and regularities from data without the need for explicit rules. 2. Adaptability. Connectionism emphasizes the adaptability of systems. Neural networks can adapt to new data and tasks without the need for reprogramming, making connectionism more flexible when dealing with complex and dynamic environments. 3. Generalization ability. Connectionist models demonstrate a certain degree of generalization ability during the training process, allowing them to generalize to unseen data. This enhances their performance in tasks with variations and noise. 4. Parallel processing. The parallel nature of neural networks enables connectionist systems to handle multiple inputs and perform multiple tasks simultaneously. This contributes to improving system efficiency and speed. 5. Nonlinear mapping. Connectionism introduces nonlinear mapping, enabling models to learn and represent more complex relationships and patterns. This is crucial for handling highly nonlinear tasks. 6. Self-organization. Connectionism systems possess a degree of self-organization, automatically adjusting the structure and weights of neural networks to adapt to the distribution and features of input data. 7. Applicability to large-scale data. Connectionism excels in handling large-scale data with the development of deep learning. Connectionist models have achieved significant success, especially in fields like image recognition and speech recognition. 8. Hierarchical abstraction. Connectionist models in deep learning adopt hierarchical abstraction representations, allowing systems to extract and learn features layer by layer, achieving higher level cognition. These advantages have led to significant achievements in various fields, particularly in computer vision, natural language processing, and speech recognition. However, along with these advantages come certain drawbacks. 1. Black box nature, poor explainability. Most connectionist models are considered black box models, making their decision-making processes challenging to interpret and understand. The complex internal structures and learned representations hinder the explanation of how the models work, limiting transparency in decision-making. In some applications, especially those requiring explanations or compliance with regulations, interpretability becomes a significant issue. 2. Data requirements. Connectionist models typically require large amounts of data for training, especially deep learning models. In some domains, acquiring large-scale labeled data may be expensive or challenging, limiting the application of connectionism in certain tasks. 3. Computational resource demands. Deep learning models often demand substantial computational resources for training, including high-performance graphics processing units, GPUs, or specialized hardware. This increases the cost of training and deploying these models. 4. Sample dependency. Connectionist models exhibit a strong dependence on the distribution and features of training data, limiting their generalization ability to unseen data or domains, especially when data distributions change. 5. Overfitting. In scenarios with significant data noise or small datasets, Connectionist models may be prone to overfitting, performing well on training data, but poorly on new data. 6. Lack of common sense reasoning. Connectionist models often lack the ability for common sense reasoning, struggling with tasks that require understanding complex contexts and strong reasoning abilities. This is an area where symbolic AI excels. 7. Concept drift. When the distribution of input data changes, connectionist models may encounter concept drift, leading to a decline in model performance. These drawbacks, along with the advantages, provide a comprehensive view of the strengths and limitations of connectionism in the field of artificial intelligence. Firstly, although modern neurophysiology has made significant discoveries in the study of the nervous systems of humans and animals, there is currently no comprehensive theory that fully explains the workings of the biological nervous system. Instead, connectionism continues to attempt to uncover and understand the mysteries, but it has not reached a complete level of comprehension. This might be the fundamental reason for its black box nature and poor interpretability. Moreover, neurophysiology has not completely revealed or discovered various mechanisms of the biological nervous system, which may be the reasons for other shortcomings, such as overfitting, sample dependency, concept drift, etc. Thirdly, the current methods of simulating neural networks using CPUs and GPUs are evidently contrary to the true workings of the biological nervous system. Until people find a suitable implementation, the demand for computational resources may always be a problem. Neuromorphic computing with memristor devices being considered a breakthrough direction is something many believe in. Despite various drawbacks, connectionism is a popular research direction in the field of artificial intelligence today. With the help of Moore's law and the efforts of computer hardware manufacturers, especially graphic hardware manufacturers, connectionism has made significant progress in deep learning and reinforcement learning, demonstrating remarkable intelligence. Let's review some of these achievements. Together, deep learning, connectionism has achieved tremendous success in the field of deep learning. Deep learning refers to the use of deep neural networks for learning and inference. This approach allows models to learn complex feature representations from large-scale data and is widely applied in tasks such as image recognition, speech recognition, and natural language processing. The rise of deep learning marks a significant breakthrough for connectionism in pattern recognition and perception tasks. Convolutional neural networks CNN is a deep learning architecture specifically designed for processing grid-like data such as images. It extracts spatial hierarchical features by using convolutional kernels with shared weights on input data and has been widely used in image recognition, including applications in AlphaGo. Recurrent neural networks run is a deep learning architecture suitable for sequence data, equipped with memory units capable of handling sequences of varying lengths. It has played a crucial role in fields such as natural language processing and speech recognition, allowing models to consider contextual information. Generative Adversarial Networks (GAN) is a deep learning framework consisting of a generator and a discriminator that engage in a game to generate realistic data. GAN has achieved great success in tasks like image generation and style transfer. Transfer learning is an essential technique of connectionism for addressing data scarcity or imbalance issues by transferring knowledge learned on one task to another related task. Models can more effectively utilize limited labeled data. Reinforcement learning, connectionism has made significant contributions to the field of reinforcement learning. Deep reinforcement learning methods like deepqlearning, deepqlearning, and deep deterministic policy gradient have demonstrated outstanding performance in gaming and robot control. Self-supervised learning, a form of unsupervised learning where models are trained by generating their labels, has seen breakthroughs with connectionist methods, especially in speech recognition and image representation learning. These achievements demonstrate the success of connectionism in various application domains, driving the continuous development of artificial intelligence technology. The methods of connectionism show strong potential in handling large-scale and complex data, addressing perception tasks and solving decision-making problems. Leveraging the aforementioned research results, we have entered the industrialization stage in the field of artificial intelligence, particularly in natural language understanding, speech recognition, and visual recognition. These technologies are entering everyone's life through various consumer products, profoundly changing our world. Connectionism remains a highly active research area today, with many unknowns and possibilities awaiting exploration. Simultaneously, it is undergoing rapid industrialization, with updates happening on a monthly and weekly basis. We will introduce some of the latest developments in future videos.